It's a rare condition this day and age to read any good news on the newspaper page. And love and tradition of the grand design, some people say, is even harder to find. It's the bigger love of the family.
Oh, didn't see you there. Welcome to Team BTS's project on San Diego State's Parking Structure 4 Solar Carport Project. Welcome to the top deck of Parking Structure 4 at San Diego State University. This parking structure, originally built in 1992, is a perfect opportunity for San Diego State to use open space to become more self-sustainable by installing solar panels on the top deck. As you can see here, plenty of opportunity.
The location of our project takes place at 5500 Campanile Drive, San Diego, California. This is also known as Parking Lot Structure 4 at San Diego State University. The objective of the project is to promote San Diego State becoming a leader in renewable energy. So they have deemed it necessary to install a carport over the roof of Parking Lot Structure 4. The university has selected BTS for assistance to determine the best and most cost-effective solution. These are our basic design specs. Total area, 50,544 feet squared. Number of columns, 40. Beam selection, W14 by 61 and W14 by 342. Solar panel selection, 3.25 feet by 6.5 feet at 300 watts. Number of solar panels, 2,376. These are the code references used to create our design criteria. 2016 California Building Code, ASCE 7-10, ACI 318-14, AISC 360-10, General Design, and AISC 341-10, Seismic Requirement. So upon the initial survey of the existing site, we discovered some minor issues with the column. The damages are very minuscule and will not affect the integrity of the structure, although BTS does have an allowance set aside to repair any damages.
To erect our solar carport structure, we plan to take full advantage of these 30 by 30 inch concrete stub columns here on the top deck of PS4. We are going to use this as our point of connection for our new steel columns. Opposite of these beams, we plan to also utilize the existing safety wall structure as another point of connection for our new tube steel structure. Being on the top deck of the parking structure, we plan to take full advantage of the exposed stub columns. Each column is 30 by 30 inches, giving us a maximum of 900 square inches to work with for a base plate. We intend to cover the entire footing with a half-inch thick A36 steel base plate. Per our calculations in accordance to the AISC Steel Design Manual, both area and thickness are larger than our calculated minimum. In terms of attachment, we plan to utilize 3/4 inch ASTM F1554 anchor rod systems that penetrate 10 inches deep into the existing column. When placing these bolts, it is important to consider the existing rebar arrangement. Per the parking structure as-built that we were provided, an edge distance of 4 inches will avoid any issues with the existing rebar. As for the HSS column, we plan to apply a 1/4 inch fillet weld all around the base of the column to attach it to the base plate. The safety wall connection is very similar to the column connection. However, the safety wall will feature a half-inch thick 12 by 12 inch base plate with both spaced with an edge distance of 2 inches.
The steel framing of the solar panel array will be made up of wide flange beams. The beam selection was made under the assumption that the failure mode for the beams will be bending. A live load of 20 pounds per square foot was used via AISC code for a live roof load. A solar panel dead load value of 5 pounds per square foot was given to us from KPFF. These loads were combined and multiplied by the appropriate tributary widths to come up with unit distributed loads for each beam in question. The distributed load and length could then be used to calculate for a maximum moment, specifically by using the formula W times L squared divided by 8, with W equaling the unit distributed load and L equaling the length of the beam. Once a maximum moment was calculated, an assumed yield stress of 36 ksi would then be used with a factor of safety of 1.5 to compute an allowable bending stress of 24 ksi. This leaves us with a value for bending stress and maximum moment. These parameters can then be used in the equation bending stress equals maximum moment divided by section modulus to calculate for a specific section modulus value in cubic inches. The value can then be taken to the AISC steel beam tables and used to select a steel beam with a section modulus that is equal to or greater than the specifically calculated value. This process was used to select all of the major beams in the framing arrangement, and the major beams selected include W14 by 61 beams and W14 by 342 beams.
The A. Steadman & Sons purlin manual was used to select the purlins for the framing. The main parameter that went into the purlin selection was the maximum required length of each individual purlin, 24 feet, and the spacing of the purlins, roughly 3.5 feet. The purlins selected were C225 steel channels. Once beams and purlins were selected, the column loading could be calculated for. The load supported by the column included the weight of the solar panels, the purlins, and the beams within the tributary area of each individual column. The value obtained was roughly 87 kips per column. This value, with an imposed column length of 9 feet, was then taken to tables in the AISC Steel Construction Manual to determine an appropriate column to support the designated load at the designated length with a factor of safety of 1.5. The selected column was an HSS-3, half a foot in width, 3.5 feet in depth, and 3/8 of an inch thick at 9 feet vertical in length. The bolts were selected by calculating for the maximum shear stress experienced in each connection and referring to the AISC Steel Construction Manual to select a bolt arrangement that could withstand the given shear stress with a factor of safety of at least 1.5. Assuming 4 bolts per connection, the resulting selection was a Group B thread connection X 7/8 of an inch diameter steel bolt.
This project has a price tag of just over $4.1 million. The pricing includes general condition costs of a fully staffed project management team, repairs to existing concrete structure, restriping of all parking stalls in the top deck, and the cost to furnish and install a turnkey photovoltaic system. Quantity takeoffs were performed using PlanSwift professional estimating software and using current labor and material rates. BTS has an aggressive 3-month schedule with the work to be completed over the summer 2019 break. By delivering the steel to the site and adding a second shift for welding the over 60 beam splices, BTS will ensure that the steel erection is fast, safe, and efficient. A team of electricians immediately after the first purlins are set will begin installing the nearly 2,800 solar panels. This will ensure that the project will be completed on time and ahead of the fall 2019 semester. By establishing a laydown area on the ramp section of level 8, steel shapes will be readily available for installation.
With the total cost equating to $4,128,705 and the power generated per year equaling 2,120,650 kilowatts per year, the payback period will be 7.73 years. As a closing remark, BTS would like to thank KPFF, John Prince, and Jim Healy. Thank you.